The gating system is bifurcated into two types. First is based on location, and another one is based on pressure. Based on location, we have top, bottom, parting, and step gating system, while based on pressure, we have pressurized and non pressurized type of gating system. Now let's discuss each and every one of them with proper formula and proper derivations. First being the top gating system, which is based on location of the gating system. In case of top gating system, the in gate is at the top of the cavity, and hence the molten metal will enter the cavity from the top. This is what a top gating system is. In case of top gating system, the pouring time is given by V suffix C by volume flow rate, where V suffix C is the mold cavity's volume, the volume of the cavity basically, and volume flow rate is given by A suffix C into V max, where A suffix C is the choke area, which is the minimum of the gating ratio, that is the minimum of the sprue area or the runner area or the ingate area. The minimum of all these three entities is considered as the choke area. Now why we are taking maximum velocity in case of top gating system? Because molten metal is getting enter into the cavity right in the top, hence it will have maximum potential energy there, which is in turn given by under root 2gh, in which h is the height of the molten metal maintained at the pouring basin itself, as shown here. Then we have bottom gating system. The setup for the same is drawn here. In case of bottom gating system, we have maximum as well as a minimum velocity of the molten metal. This is because the molten metal enters the cavity with the maximum velocity, but as soon as the cavity is getting filled and the molten metal reaches the top of the cavity, the velocity of the molten metal reduces considerably, and this is purely due to the height difference. Here height h is the height at which the molten metal is maintained in the pouring basin, and h dash is the final height of the molten metal when the cavity is completely filled. V suffix c remaining the same, that is the mold cavity's volume, and A suffix c, the choke area, is also the same, that is the minimum of sprue area, runner area, and ingate area. However, the pouring time formula slightly changes. Here, instead of writing V suffix max or V max, just like in case of top gating system, we are writing here V average, because a average of both maximum and minimum velocity has to be taken. Here the maximum velocity is at the bottom where the molten metal is entering. It is given by under root 2gh, and h is the height at which the molten metal is maintained in the pouring basin. And as soon as the molten metal reaches the cavity, the top of the cavity basically, its velocity is considerably reduced, and it is given by V minimum is equal to under root 2g h dash, and h dash is the height at which the molten metal is maintained in the pouring basin to the molten metal when it reaches the cavity's top place. And hence the average velocity is given by V max plus V min, that is maximum velocity plus minimum velocity, by 2. The pouring time in such type of gating system, in bottom gating system, is higher as compared to the top gating system, because here velocity reduces overall, because we are taking average velocity, not the maximum velocity. The characteristics difference between the top gating system and the bottom gating system is given here. In case of top gating system, we have lower pouring time, whereas in bottom gating system, the pouring time increases. In top gating system, since the velocity is maximum, there will be more chance of turbulence. However, in bottom gating system, the chances of occurrence of turbulence reduces. In case of top gating system, there is more impact loading. That means sand erosion will increase. However, in bottom gating system, there is a lesser chance of sand erosion, which is again due to lesser velocity. And then in top gating system, temperature gradient is favorably maintained. However, in bottom gating system, temperature gradient is unfavorable. Next comes the parting gating system. In parting gating system, the cavity is divided into two halves. The bottom half of the cavity, which is denoted by 1 here, acts as a top gating system, whereas the upper half of the cavity acts as a bottom gating system. And hence, the corresponding velocities will prevail. In case of section 1 here, that is the bottom half of the cavity, the velocity that we will have would be Vmax, because in the bottom half or the section 1 of this particular setup, we are dealing with a top gating system type of scenario, and hence the velocity will be maximum. Whereas in the upper half, the velocity would be termed as the average velocity, and hence the pouring time can be calculated as Pt1 plus Pt2, that is Vc1, that is the volume of cavity 1, that is the volume of the section 1 of this setup, and Vc2 would be the cavity's volume of the section 2, and hence this is the complete formula for the pouring time of parting gating system. Here again the mold cavity volume remains the same, that is V suffix c, and it is in turn Vc1 plus Vc2. The pouring time in case of a parting gating system, it lies between top gating system and bottom gating system. The pouring time is higher than the top gating system, but it is lower than the bottom gating system. However, the turbulence is exactly opposite. The turbulence in case of parting gating system is lesser than the top gating system, but it is more than the bottom gating system. And all the other properties of the parting gating system lies between top and the bottom gating system. Next, let's understand the type of gating system on the base of pressure. Here is the setup for a pressurized gating system, in which the runner is taking the shape of a nozzle, and hence the molten metal will go inside the cavity in a pressurized manner. That means we have maximum velocity in the ingot. The CSA, that is the cross-section area, is reducing towards the mold cavity, as you can see here, and hence back pressure will be maintained because there would be restriction of molten metal flow. There would be lesser chance of aspiration because of the shape of the runner, and due to high velocity, there would be also higher chances of turbulence and sand erosion. And hence this kind of gating system, this kind of pressurized gating system must be used for low density metals. And last but not the least is the non-pressurized gating system, in which the runner takes the shape of a diverser, or basically a diffuser, and hence the molten metal enters the cavity with lesser velocity. the cross-sectional area is increasing as you can see here. There would be lesser chance of turbulence and there would be lesser chance of sand erosion. And this kind of gating system is most suitable for low density metals like aluminum and magnesium.